the open house of the Division of Computer and Information Science. I'm very pleased to be able to introduce our first speaker of the afternoon, Professor Michael Littman. Michael got his PhD from Brown University, spent a number of years on the faculty at Duke, where he actually received one of the university's Distinguished Teaching Awards. So we're in for a wonderful talk today. He came back to New Jersey to work at AT&T Labs a couple of years ago, and as you know, the telecom industry has been having difficulties. Their loss was our win. We were able to recruit him to our faculty about a year and a half ago, and he started up an enormous amount of energetic efforts in areas of machine learning and robotics. You may have seen his robotic dogs outside performing for your benefit. And so I'm very pleased that he's on our faculty, and I'm very pleased to be able to introduce him all to you. Michael Littman.
Wow, thanks. I didn't know you were in for a treat. I haven't seen this talk, so we don't have to believe him on this one. So it's a great honor to be able to give this presentation to you. I'm the first of three faculty. I don't usually talk into microphones, so I'm not very good at that. But my voice is going. I'm going to try without. Can you hear me? Yes. Can you hear me now? Speaking of the telecom industry. So the first of three faculty talks. The U.S. News and World Report, when they rank computer science departments, includes three subdivisions of computer science: AI, systems, and theory. And so you essentially have one talk from each of those areas, but there's a lot of other work going on here at Rutgers that you should learn about in various ways, talk to the faculty, check out the web pages, and so forth. So I am the artificial intelligence speaker, and I wasn't artificially intelligent enough to know that I should go first, but I am anyway. I want to talk about the learning path to artificial intelligence, and this is basically an introduction to some areas of artificial intelligence if you don't already know about them, but also kind of a way of me getting to tell you about some of the work going on in my new lab, the Rutgers Laboratory for Real-Life Reinforcement Learning, or RLQ. And I want to thank the members of the lab who worked really hard doing the work that I'll tell you about, as well as putting together the presentation and the demo and the poster, which finally came in. All right, so AI. So a reasonable question might be, why study artificial intelligence? And why study it as part of computer science, even more so? So what motivates people to study artificial intelligence? Well, there's a classic one of, we want to make your plastic pal who's fun to be with. This is Marvin the robot. So one goal is to just make artificial intelligent entities because, well, for the same reason that we might want to have people around, we might want to have other things like people around. Another goal might be, to the extent that we can build artificially intelligent entities, we might better understand the intelligent entities that we already have lying around the house. So understanding humanity is another goal. Another thing you can do is just use the kinds of technologies that we've been developing to solve challenging problems in computer science, like scheduling, for example. Or create useful tools that we don't have today, like smarter elevators. Or maybe really what you want to do is produce a decent movie. Now, of these various goals, some of these are being worked on more actively than others. I think this last one has basically been given up as completely intractable. But things like creating useful tools and solving challenging problems in computer science are very actively being worked on. I think there's a lot of successes that AI people can point to of ways we've influenced science and technology. This understanding humanity thing is kind of an ongoing process. Since we don't really kind of understand humanity yet, you can't say that we're finished, but in some sense I think computer science and AI has made a lot of contributions to our understanding of how the mind works. And not so much make your plastic pal be fun to be with. So what's up with that? So creating human-level AI was one of the significant motivators in the early days of why we want to have AI in the first place. We'll have smart computers, smart machines that would be able to interact with and help us with things. And yet lately this has not been an active goal in academia. So what is going on in academia? Most of the research, if you think about AI as being defined in the way that you might think about it from the movie or what have you, that's not most of what's going on these days. Most of what's going on is more focusing on narrow competences, trying to get a computer system to do something fairly specific. You make it into something, a computer science type problem. You define what the inputs are and what the outputs are, and you just figure out what you need to map the inputs to the outputs. And that's actually been remarkably successful, but I think one of the big computer science type questions about artificial intelligence remains unanswered at this point. And I would state it this way. We don't know what kind of information we need to put into our programs to make them intelligent. Or phrased from maybe from a software engineering perspective, how ought we program intelligent machines? So I don't know. I have my idea, and I'm going to try to convince you that my idea is reasonable, if not correct. But let me, to help motivate that, let me say a little bit about the ways that people have pursued this goal in the past. So this is one particularly impressive achievement. This is Honda's Asimo robot that walks. This is an actual robot, not a very skinny man in a suit. And not only can it do impressive walking, but it can deal with overacting human beings without killing them, the way that you might expect from a science fiction movie. It walks remarkably realistically, many degrees of freedom. It's really quite amazing and impressive. It can walk downstairs. And so, in some sense, it looks like maybe we're pretty close to the plastic pal idea. But the fact of the matter is that there's still quite a ways to go. Now, Asimo is actually controlled by people in many, many, many ways. One is that the structure of the walk itself, the way that it's going to lift it from the knee and then extend the foot and then change its weight, all that's been programmed in by people. People have decided what the walk ought to look like and have worked for many, many years to hone it. At the same time, its reactions to perturbations are programmed in as well. So it's not just a series of motions. It's not quite that simple. You actually have to deal with the fact that it can be changing its weights as it goes. And those perturbations are also, the reactions are programmed in. And in fact, in that demonstration that you just saw, where it should walk, when it should walk, is all controlled by technicians, and as it turns out, puppeteers. They've hired professional puppeteers to stand back at the control center and tell the robot where to go when to lift the arms, when to wave, and so forth. That's not it reacting on its own. And if you notice the way that it was actually doing the walking, it was this kind of highly stable walk, right, where you can't fall down. It's not, it's some kind of walk where if you stop in the middle of it, you fall on your face, and I know because I've done that before. The kind of ballet stuff that you saw here. So this is not really a solid problem. But you can say, okay, well that's not fair. Before you learn to walk, you probably should learn to crawl. So there is some work going on to try to build crawling robots. These are the Ivo robots. You can see them out at our demo station. We have robots like this. These particular robots play soccer for the University of Texas, Austin. You can see them in their uniforms. Soccer ball fashion. This walking behavior is what you just saw was programmed in by people, and then over a series of trials, it was honed automatically into this walking behavior here. This walking behavior is actually the fastest known gait for this particular kind of robot, and it was created to a large extent through a learning process, through an optimization process, without direct human intervention. Now, that being said, the gait itself, again, which limb is going to get lifted when, and how much you're going to extend from the elbow and so forth, the overall pattern of that was defined by the programmers, but the details of exactly how much weight to put on and how many angle degrees to extend the joints and so forth was then optimized in this automatic process. So, I think it's quite impressive as a start, but compare this to human crawling. It turns out that there's, from web searching, I was able to identify 7 different types of crawling behavior known. There's the standard diagonal crawl. This is my nephew. Some kids don't crawl, they just roll where they want to go. Other kids do this thing called bottom shuffling. If you've never seen it, it would blow you away. It's really fascinating. The kid sits on the ground and kind of pushes with his hands. It's remarkable, and it does terrible things to clothing. Some babies do the commando crawl, where they're down on their belly, which is great for infiltrating enemy lines. So if you look at what babies do, you might start to think, I would start to think, that maybe it's not so much that we're programmed to crawl. Maybe what we're programmed for is the desire for movement, right? These babies they want to go someplace. We want to go someplace. There's things we want to do, and the details of how we go about doing it are subject to some other external process, which we're going to call learning. So if you believe this, if you take this to heart, you might then posit what I call the reinforcement learning hypothesis, which is you want to create intelligent behavior. Intelligent behavior arises from the actions of individuals seeking to maximize their reward signals in complex and changing worlds. So, if you think about this as a call to arms for a research program, you might want to focus on 2 different possible things. One is to tell the system what it is that it's trying to do in the world. You have to identify these reward signals, where they come from, what are they, how are they going to be computed from sensors and so forth. And given that, then the behavior of the entity itself, the agent, the decision maker, is to search the space of possible behaviors for ones that maximize these reward signals. So both of these are really important parts of the equation, and the contention here is that if you can nail these down correctly, then all the rest follows, right? Intelligent behavior, going to McDonald's when you're hungry and don't mind a little extra salt, all that just falls out naturally from these basic tenets that we as computer scientists need to solve this problem and solve this problem, and the rest is about teaching the baby robots to do whatever it is that they need to do. So this is a hypothesis. It may or may not be true, but I'm going to take it as being true and proceed from there, because I got to do something. And I'm really tired of programming all these behaviors in. All right, so the way that this has been studied in the field of reinforcement learning is by setting up the following computational problem. We're imagining a decision maker that's interacting with an environment, and what it gets to do is it learns the state of the environment at each moment in time, is transmitted into the robot through its sensors. It can choose some kind of action, which is going to influence the environment, change the state, but it's also getting this reward signal, and its motivation, what it's trying to do is choose actions as a function of states to maximize reward. And these are sum of rewards into the future, so it's not just trying to greedily maximize its pleasure at the moment. It might also want to do something that may be annoying now, but sets it up for something pleasurable later, like preparing a very long and difficult talk with the payoff of being that you actually get to give the talk. That's all within this kind of framework. So, just to make this a bit more concrete, I want to tell you about one particular application that you can imagine, we can get our heads around, that can be formalized, and be thought of as a computer science question, and how we might go about solving it. So this is my attempt at drawing a down view of those Ivo dogs. And imagine that what we've done is we've programmed them so that they can take any of two possible actions. They can turn left, they can turn right. The state of the world then, at least as far as a robot is concerned, is its orientation, which way it's facing. All right? And its reward signal, what it's trying to do in this case, in this example, is see its pink ball. Now, it turns out that the robots come from Sony with these pink balls, and the particular color of pink that they chose is very easy to recognize in cluttered scenes. So this is something that was very easy for us to program in, or for Dave to program in, as the case may be. And so if we take this to be the problem, what the robot needs to do is figure out which way to turn to see the ball, say, as quickly as possible. All right, so we can view this as a shortest path problem. Really, it's not about a robot in a world. It's really about a set of states that the system can be in, one state that is a goal state, and transitions between those states, which are the different actions that it can take. And it becomes just a problem of how do you choose actions to minimize the steps to the goal? How do you make the shortest feline path to the target? And if that were the whole story, then my talk could end early. But it's actually significantly more complicated than this for a bunch of reasons. So let me say a little bit about what those reasons are. Even in this simple problem, some of the tough issues that come up are, one, these actions, if you actually program this on a robot or any other kind of real-life scenario, the actions are stochastic. And in the case of the robot, it can under or overturn. When it turns left, it might turn too little or too much. It's inconsistent, the way that it actually works. The graph that I drew before is actually not known to the system when it starts up. So that needs to be learned. The agent needs to explore its environment. The sensors themselves, there's no sensor on the robot that says you are now in state 8. Though it would be helpful, and if anybody wants to work on that problem, I'd welcome it. Nevertheless, we do have sensor information, generally the information coming into the robot's camera. But literally, these sensors are extremely rich, and you literally never see the same thing twice. So even when it is at the same orientation multiple times, it never gets exactly the same camera image. So we can't just, say, hash them to some state value and then solve the graph problem from there. In addition, not only is there too much information in the sensors, but there's also too little. There are situations that the robot can be in that look pretty much the same, but are different, right? It can be facing this way and see that hole in the wall, and facing this way and see that hole in the wall, and oh, there you are. Okay, and not know which way it's really facing and what it ought to do next. And in addition, if you actually try this, and this is happening in the hallway here, the world is non-stationary. That there are things in the world that are changing, details that are changing over time. So even though, basic tenets of physics aren't changing from moment to moment, if the robot's dependent on seeing a person's legs in a particular orientation when it goes to look for the ball, and the person moves one foot to the left, something's changed and the robot needs to deal with that. So the emphasis of our lab is trying to work on these different challenges with the overall goal of getting to reinforcement learning type behavior. So I want to tell you about some of the projects in the lab and how they're attacking these different problems that I just mentioned. First one I want to say a little bit about is this idea of learning by way of efficient exploration. So now when we place a robot or an agent, decision maker in some kind of situation and it doesn't know the state space yet, it doesn't know the graph, it needs to efficiently explore to try to identify what the way things work in the world. And at the same time, it needs to exploit the knowledge that it's developed to best reach its goal. So the way that we're doing this is that we have the decision maker as it moves through the world. It builds an approximate model. It says, when I'm in this kind of situation, I do this kind of thing. This is the sort of thing that happens next. But I'm not entirely sure because I've only seen it happen twice, and it's random enough that it might be something else that happens. So instead of just believing that model implicitly, it accounts for some of the uncertainty in the model. And then, in addition to the rewards, the external rewards of, say, seeing the ball, there are internal rewards that are generated, paying off curiosity. Right? If the dog gets into a situation that it doesn't know a lot about yet, even if it doesn't get a lot of reward directly from the environment, we're giving it little internal rewards to say, "Oh, that's okay. At least you learned something." Right? So it's a natural sort of thing to do, paying off for curiosity, but it actually has a pretty substantial effect on how well these systems can explore their environment. So these are graphs denoting 3 different exploration strategies. These 2 from the literature, and this is one that we've been working on, where this is the time axis, the amount of experience, and this is the accumulated reward that the system was able to gather. And what you can see is this method that takes into consideration model uncertainty and uses that to cause it to explore parts of the environment so it can learn more about them and learn better how to get additional reward, ends up with roughly twice the accumulated reward out of in these 2 time steps. So we're exploring this method for exploration. The question of rich sensors. How do you do decision making when you're not told specifically what state you're in? We're looking at it in a number of ways. One, the camera images that I mentioned before, but we're also looking at GPS data. So I have a GPS device that I bought that just records where my car is all the time. And this is me driving around over a period from like November to middle of December, something like that. And you can see all sorts of things here. You can see Route 287 well worn as I drive back and forth between Rutgers and my house. But you can see things in Morristown that I have to go to, and various kinds of roads, my parents' house in Pennsylvania, and my in-laws' house in Freehold. You can collect all this sort of data, but then you want to ask, well, what sort of things can you do with this data? One is, you might want to do path planning. You might want to say, what's the best route, given what we know about the way the world works, to get from Morristown to Princeton? And I've never driven that route, but I've driven all the little segments of it, and just like a robot exploring its environment, these little bits of knowledge about the way that this location is near this location, driving on Route 287 at 5 p.m. is, say, slower than driving on Route 206 at middle of the night. All those sorts of facts are stored in the data in some way. And so what we'd like to do is squeeze them out to the point where we can do efficient path planning in spite of the fact that we have these rich sensor information. We're starting to apply exploration in this case. We haven't connected that up with the GPS device because I already get lost enough. I don't need some system telling me, why don't you try making a left here and see what happens? So I haven't really thought of connecting those 2 things up yet. But we are doing pretty efficient exploration in continuous spaces. And another area that we're starting to do exploration in is text filtering. So here's the question. Here's the problem of, imagine that the computer system is getting a stream of documents to present to the user, and the user, to help provide motivational signals, provides reward and punishment to the system for delivering documents. So you can imagine that it's email, and spam messages annoy you, and so you hit the bad computer button whenever you get spam, but you hit the good computer button whenever you get a message that you actually did want to read. And now the system, trying to maximize its cumulative reward over time, should try to distinguish what's spam and what's not spam. Now, of course, not delivering a message at all doesn't get it any reward, and so there is a danger that it'll just stop delivering your mail altogether if it starts to think that you're spam. If spam pisses you off enough, it will stop delivering your mail. So you probably want to have a higher reward for delivering a document than for not delivering a document. But nevertheless, you do have this exploration-exploitation trade-off. The system can't just guess what's spam and what's not. It's going to have to deliver some messages that it might think are spam early on so that it can hone its spam model. And so we did some early experiments with real document collections trying to figure out, well, do you get any kind of benefit? Right. So my computer just ran out of batteries. So I think I can get it started quickly, but otherwise I may need to just tell you the punchline. Where is the Oh no, you see that it's plugged in. One side. So this is a learning episode, right? Yes. Nice that it gave that helpful warning. Oh, son of a gun! We're up and running again. All right. 3 cheers for. All right. Good. All right. So moving off of this slide because it's scaring me now. Another area that we're doing learning is in non-stationary environments that change over time, and we're actually fairly inspired by some work that's going on in cognitive science with actual animals. And one of the things that they've noticed in the lab, Randy Galston and a bunch of his colleagues, are that, well, actually psychologists have known about this for some time. If you give a rat two different choices of things that it can do, and one has a higher payoff than the other, then it tends to apportion its investment in those two options proportionally to how much they pay off. So the bigger cheese gets more visits than the smaller cheese, but they both get some amount of visits. But what's interesting is if the rat's doing this and you suddenly switch the cheeses on it, it very quickly notices that something's different and nearly instantaneously changes its behavior to match the new way that the world works. So, based on this observation, Randy and others have proposed a change detection algorithm. What might rats be doing to figure out that the world has changed so that they can change their strategy? And his change detection algorithm seems really great, so we're trying to adopt it for use in some computer science problems. One of which is your laptop runs, it's trying to minimize battery usage so that doesn't happen. And it's used in different ways at different times, so it ought to have different strategies at different times. If I leave for going to dinner, I'm not using the disk at all. It should be using a different power consumption strategy than if I'm actively doing something. And it ought to be able to detect that these changes are happening and respond to them appropriately. So we've just started with this. We're taking some real data off of disks, and you can see in this particular case, there's a series of disk accesses, and then it basically goes flat. Basically, the disk was being used, and then it was not being used anymore. So a natural thing that computer systems do is either to have some kind of fixed cutoff to when to turn off the disk, or maybe if you're lucky, it'll average access times over some fixed window that's sliding. But it doesn't make much sense to slide an averaging window across a discontinuity like that. And so what Galston's algorithm that he proposed for rats does is it finds that cusp, it finds the change point, and averages only from the change point forward. And so you can see here's two algorithms. The green algorithm is doing this averaging thing, and what it does is it very slowly starts to come back down to the true prediction, whereas the red algorithm is constantly looking for the change. It takes it a couple instances after the change to notice that there's a change, but as soon as it does so, bam, it just locks onto that pattern and makes very good predictions after that. So this is not at the moment embedded in any kind of computer system, but that's what we're moving towards. All right. I also mentioned partial observability, the idea that the robot might mistake different situations for looking the same as one another, and we're using instance-based methods to try to handle that. One particular example that I'd like to tell you about, because it worked out very nicely, is learning a network troubleshooting policy. So here the idea is that the learner is embedded in a computer that's on the network, and occasionally something goes wrong in its network settings and causes it to lose contact with the network. And its job is to, as quickly as possible, get the computer back online. And what it can do is it can run tests like ping or doing a DNS lookup, and it can run repair actions like renewing its DHCP lease or restoring its network settings from some cache settings, or running some external, more expensive program that tries to fix the IP settings to something reasonable. And its job is, even though it doesn't know what the current state of the world is, right? It just gets woken up. Excuse me, the network's not working. And there's some people here who get woken up that way. Excuse me, the network's not working. And so it has to, as quickly as possible, make the network better and go back to sleep. So what this system ended up learning after 95 failure episodes is the strategy that you see here.
What does ping IP?
Ping IP. So each of these actions, either these dark actions here are repair actions. They either make things all better or they don't, and you can find out which one happened. These other actions just give information. So
How do you explain that?
So ping IP in particular, it runs a ping. If the ping returns in some fixed amount of time, it returns a 1. If there's no response to the ping, it returns a 0.
If you're not even pinging, what's the point of doing DNS?
If you're not pinging, no, this is a decision tree, right? So it starts at the top. It runs ping gateway. If ping gateway fails, then it tries to ping its IP address. If that fails, it does a DNS lookup. You're saying, why would it do a DNS lookup? I have no idea. This is just what it does. Is Nishkam here? Why does it make sense?
Yes.
It makes sense? How does it make sense?
If you're not even getting a ping, why would you do a DNS lookup? If the network is slow, what can you do?
So basically, it's argument where you want to choose the next action to perform that might get better knowledge of what repair action could be done.
Right, but what Badri is saying is if we know the ping's not working, the DNS lookup can't work.
Yeah, that could be some.
But it's clearly not true because it learned to do something when it succeeds.
No, you try to bring an external IP. You should not necessarily have ping IP fields.
It's picked some particular address. It's hard-coded with some address on the network. If it can't reach that address on the network, it could be that the network's down, or it could be that computer's down. And it can't distinguish between those two, and so it runs an additional local test to see if we can reach the DNS server. I'm saying this stuff even though I'm an AI guy, and I'm not sure that I believe it, but it had a reason for doing this. And I can show you the numbers. But anyway, what it ultimately does is it figures out if the problem is that something made the DHCP lease go away, or if it's something corrupted the other IP settings, and it just repairs them from working settings that it already knew about. And yeah, so that's what it ends up learning. That's what it ends up doing. This the way that we actually did these experiments is instead of just waiting for failures to happen, we had a separate program running on the computer that would corrupt the network settings every 2 minutes, and then wake up this guy and say, "Okay, your turn again." And this particular strategy that it learned, we could probably come up with something like this by hand. But in fact, if we had changed the distribution of failures, or if we were running on a real system and not simulating, and not generating the failures ourselves, it might have learned something quite different. It might be that it's almost always the DHCP lease, in which case it would have learned a policy that would put that at the top. First do that, it's probably going to work, and only if it fails should I bother doing all these other tests. So this is actually attuned to the distribution of failures that actually occurs, and their cost as measured in the network. And one last thing to mention is some work that we're doing on, given that we're going to try to do planning in these complicated environments, how do we, and learn about them, how can we represent what we learn about very complicated environments? So we're looking at this probabilistic planning domain definition language as part of the 2004 International Planning Competition for specifying these kinds of domains and seeing how well we can solve them. All right, good. All right, I'm winding down. There should be some time for questions. So this is where things are now. This is our future work. I guess very future work is to really try to get this learning framework worked out so that we understand really how it should work, how things should plug into it, with the idea that other aspects of intelligent interaction need to be plugged into this in some way. Instead of having a bunch of different separate systems that have independent competences, we need some kind of core thing that's going to be making the decisions, and all the decisions it has to make should probably go through that in one way or another. So you want to do better vision than we're doing on the robots at the moment. You want to be able to handle speech and language, or problem solving, or creativity, abstract reasoning. They should all hang together in some kind of a unified way. And I think this kind of learning framework is going to be able to serve that purpose. And so that's what we're continuing to push on in the lab. Thanks a lot. If you have any questions, let me know.
As I understand it, the problem is an overly dimensional market.
Okay.
And I just wonder, one of the things doing modeling of why the things that the mistakes that beginners make is that they do much too far beyond the environment, that most of the things are really irrelevant.
Right.
And you want to get the right environment. You have a highly simplified view because there are only these things that are really relevant. And have you looked at ways of doing that kind of simplification?
So the state of the art at the moment for building these kinds of learning systems is a person thinks about the problem really hard and models it at just the right level. Right? So if you model it in too much detail, then the learning problem seems too hard. If you don't model it in sufficient detail, then it's working with its hands tied. And so it's fairly successful now. People, if they model things just right, a lot of these algorithms can work. My motivation here is to try to come up with ways of doing the modeling step, trying to take the data as it is and use the experience to make some sense out of it and find the right level of modeling. Otherwise, basically, it's our job to service these systems and keep them fed with the right information. And I'd like to get out of that loop.
What is the business with the soccer, robot playing soccer? Can you tell us anything about that?
Sure. So there's this league called RoboCup that where you can see. I mentioned that. Yeah, they're right. The soccer robots were dressed up with their uniforms. So they have this competition once a year for the past 6 or 7 years, I think. It's an international competition, though we competed in the America-only one last year. And they have a bunch of different leagues. We competed in the leg league, so they were using the Sony Aibo robots, and they play soccer 4 on a side, back and forth across the field. It's highly adorable, and I don't know. I'm not so into sports, but I really enjoy watching the robots do this. I can see why people like sports. Yeah, it's robotic. If somebody invested in them, I programmed that robot. We at the moment, we tried this one time to compete in it. We backed out of it for the time being because it was very difficult to do actual research in that setting. All these teams work day and night just to program the robots to do something in a particular way, and so they follow these instructions pretty much in detail. It's hard to do learning work, and so what we want to do is back off a little bit, see if we can create robotic systems that can learn much more effectively, and then we'll just go and kick everybody's tails. So we'll be back.
I'll also point out that the team that he entered was the #1 newcomer team in the competition for the whole country, and he's backing off of that.
North America.
North America.
Yeah, well, we got trounced in the so this is a joint effort with Columbia and Brooklyn, and they went to the World Cup and didn't do quite as well there.
Give me some scores. What were the scores?
Oh, I don't know. CMU beat us like 11-1 or something. They've been doing this for a long time.
Just for context, CMU has won international competitions in some cases without allowing their opponents to get any goals.
We scored.
Program robots.
What's that?
Now, high school level,
Yes, that's been going on as well.
how advanced have you gotten in the field of artificial intelligence? Like, how far have we gotten?
So it depends on your metric, right? It depends what it is you're trying to measure. We're really good at chess now. Like, much better than you. You sit and listen to a talk and you've got nothing at all that can do anything like that. So that's the thing, is the focus. To make progress, people have focused on these sub-areas, and some of these sub-areas have gone quite well.
So now no human in the world can be the best chess.
No, that's not true. The top chess-playing humans and the top chess-playing programs are really close right now. I think there's probably a slight edge for the computers. But there's nobody doing research on that. They just build systems to do it. I think I'm going to get booted off the stage in a moment. But anybody who's still interested in AI and learning, come talk to me. It's the other AI faculty in the department. And thanks for coming to this one.